Hi, welcome to lesson 10.3 using chords. For today's lesson, you are going to need two pieces of blank paper. The first one is going to go glued on page 288, and the second one is going to be glued on page 289. So example number 1 is going to go here, example number 2 is going to go there, and on the next page you are going to do example 3 and example 4 right there. So pause the video, get the papers glued, and then proceed once you are ready. Alright, so I am not going to do a full formal proof for this, but I'm simply going to explain the reasons why these actually work. So for the congruent corresponding chord theorem, what you have here, it says that AB, arc AB and arc CD are congruent if and only if the chords AB and CD are congruent. So I want to explain to you guys the reason why this is true. So I'm going to redraw this diagram, make it probably a little bit bigger so that we can understand what exactly is going on here. Okay, so let me go ahead and draw the chord. Now, there's two ways to do this. You can do it going from this to this or from this to this. I'm going to choose to go from here to here. So, say for example, I have the center of the circle and I have B, I have A, I have D, and I have C. Now, if I was to draw all four of the radii, from here to here and from here to here, you would notice that you have these four. Actually, I should probably keep it the same. Okay, you have, I'll call these three. Where am I? Okay, you have these four segments that happen to be all congruent because they are the radius of a circle. Actually, I'll take something back. Let me erase these right here. I'll go backwards, actually. So if these chords are actually the same, that means that their central angle is going to be congruent. Okay, so let me recap. If you have these two arcs that are congruent, this one and this one, say that they are congruent. That means that their central angles should be the same. So that means that this angle and this angle right here are going to be congruent. Now these two triangles right here are going to be congruent because of side angle side, side angle side. So therefore, by CPCTC, you are going to have segment AB and segment CD congruent. Okay, so you have triangle A. I don't even center this. I'll call this center O. Okay. Give me 1 second. My mechanical pencil is acting out. All right. So triangle AOB is going to be congruent to triangle DOC. All right, so because of this, AB and CD are going to be congruent. Oopsie. Segment BC is going to be congruent to, the heck? I have not had my coffee yet, guys. Segment AB is going to be congruent to segment CD by CPCTC. Okay, so remember what we were trying to show here. We were trying to show that these two segments here were congruent. Now, because these two arcs were congruent, that meant that their central angles would be the same. This is why these two are congruent. These are not vertical angles, let me remind you that. Now, because the radius of the circle, they're all the same, that would make this triangle and this triangle congruent by side angle side. Therefore, this side is congruent to this side. And that is why the congruent corresponding chord theorem works. Let's take a look at the next one. Okay, the next one is a perpendicular chord bisector theorem that states that if EG is a diameter and EG is perpendicular to segment DF, then HD is going to be congruent to HF, and GD is going to be congruent to GF. So let's go ahead and make this a little bit bigger so that we can kind of see what's going on here. So you have a chord, and you have a diameter perpendicular to that chord, and we want to know why is it that F and D are going to be congruent. Okay, so the reason why is because of this. We know that the radius of the circle is the same. Okay, so this is congruent to this. Okay, so here the center of the circle, we can call it O, I guess. Okay, OF and OD are congruent because they're the radius of a circle. Also, we learned in chapter 6, I know it's been a while, that if you have a point that is equidistant to two endpoints, then this point is going to be on the perpendicular bisector. So here, OG is the perpendicular bisector of segment FD. Therefore, this is going to be congruent to this. Okay, so these two are going to be congruent. That would imply that this angle here and this angle here are going to be congruent as well. And because this central angle is the same as this central angle, that would imply that this segment, this arc right here, is congruent to this arc right there. So this right here is going to be congruent to this right here. Now, in order to explain the next one, it is a little bit more complicated. So I'm just going to, because you have to do a proof by contradiction, we have not done those. So I'm just going to go ahead and tell you guys what this theorem is. It says if one chord of a circle is a perpendicular bisector of another chord, then the first chord is a diameter. So if you have a chord that is perpendicular to another chord, this chord is going to be going through the center of the circle, making it a diameter. All right. Now, explaining that one is a little bit more challenging because you would have to do like a kind of like a proof by contradiction, and let's not confuse that right now. Okay, so for this one, in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So let's trace back and see what exactly is this theorem telling me. Okay, so if I have two chords, like the ones you see right there, C, D, A, and B, and you have the center of the circle, and you have what we call the shortest distance between the center of the circle and the chord right there. So we call that G, E, and F. Okay, so if these two here are congruent, then CD is going to be congruent to AB. So let's figure out the reason why though. Now what we're going to do is we're going to construct the radius of the circle from here to here and from here to here. So technically this is congruent to this. Let me repeat the process for this one and this one. Okay, and because they are the radius of a circle, they're also the same. So if you really think about this, all four of these triangles are going to be congruent by hypotenuse leg congruence theorem. Therefore, because the triangles, all four triangles are congruent, that's going to make this segment here congruent to this segment here, and this one, and this one. So by the segment addition postulate, AB and CD are going to be congruent. Okay? So that would be an explanation. Now, if I want to make this into a formal proof, it'll just take me a bit of time to actually do that, but we can. All right, so let's go ahead and begin our examples. So please turn to example number 1. Go ahead and copy that, pause the video, and copy that. And once you're ready, you can go ahead and continue. Okay, so in this problem, it says that in circles P and Q, FG and GK are going to be congruent, and the measure of JK is going to be congruent. It's going to be 80 degrees. So they want me to find out is what is the length of M, the measure of arc FC. So one of the things that we learned is that in the same circle or congruent circle, two minor arcs are congruent if and only if their corresponding chords are congruent. So the fact that these two chords right here are congruent is going to tell me that this arc right here and this arc right there are going to be congruent as well. And the reason why we can apply that is because the radii are the same, meaning that these two circles are congruent. So the measure of FG, not FC, FG, is going to be the same as this one, which is going to be 80 degrees. So that, ladies and gentlemen, is example number 1. Okay, let's look at example number 2. Okay, in example number 2, we have a very busy diagram. So what we have here is we have a diameter that is perpendicular to a chord, which means that this segment right there is going to be congruent to that segment right there. So if I'm looking for the distance of HK, I know the distance from N to K, which is 7. So the distance from H to M is also going to be 7. So this distance right there is also 7. So the distance from H to K is going to be twice of 7, which is 14. Because 7 plus 7 is 14. Now, for B, to find the measure of arc HK, okay, we have to remember that in the theorem, it tells me that if this is a perpendicular to a chord, it's also the perpendicular bisector. So not only are these two congruent, but these arcs, these minor arcs right here are also congruent. So 11x is actually going to be equal to 70 plus x. So what we get to do now is we get to solve for x. That gives me 10x equal to 70 divided by 10, and x is equal to 7. So now what I need to do is I need to go back and substitute that for arc HK. So HK is the whole thing. So I have two options. I can substitute in one and just double it, or substitute in both and just add them together. So I think I'm just going to substitute it on this one. So that would be 11 times 7, which is 77. But that's only this distance, okay? So 77 times 2, that's 154. So the measure of arc HK is going to be 154 degrees. All right, example number 2. Okay, so this one's an application to one of the theorems that we have, where we actually have to find a place to put a sprinkler such that it's going to water all three of these. So I'm just going to create the center of these bushes right here, mark them as points. Okay, so what I'm going to do is I'm going to create segments from those. So just create. Now we are actually going to hand sketch this. We're not going to do like a construction, even though we could. But what I actually need is I need to find out a point that is going to be equidistant to all three. In other words, I need to find the radius of the circle. So the only way to do that is by looking at the perpendicular bisector of this segment. So I'm just going to grab my protractor. I'm just going to eyeball it. I know I can do a construction, which will be a little bit more accurate, but we're just going to eyeball it right there. So this right here is my perpendicular bisector. Okay, perpendicular bisector, where this and this are going to be congruent. Let me see if I can put it in a highlighted in a different color so you guys can see what I'm talking about. Okay, so that's the perpendicular bisector of that segment. Let me highlight the original segment because I think it's hard to see in the video. Okay, so those two. So I'm going to do exactly the same thing with the second segment. So I'm going to kind of eyeball where it's going to go. That's about half. So I'm going to draw that line. That's going to be the perpendicular bisector, making that congruent to that. And let me pick a different highlighter. So what's going to end up happening is that I'm going to get a point of intersection. That point of intersection is going to be right there. Okay, so that point of intersection is what we consider the center of the circle. So because that is the center of the circle, that would imply that it is equidistant to all 3 points, because it will be considered the radius of a circle. So this distance is the same as this distance and the same as this distance, because they're all the radius of a circle. Okay, if you need any help in class understanding this, I'm more than happy to go over this problem again. All right, last example. Okay, so I'm going to zoom in a little bit on this one because it's a little bit smaller. Okay, they tell you here that QR and ST is equal to 16. So all of this is equal to 16. Now, we do notice here that the radius here is going to be a perpendicular. So because the whole segment is 16 and the whole segment is 16, I know this measurement right there is going to be 6. And this measurement right there is going to be 6. Okay. Now, CU is equal to 2x and CV is equal to 5x minus 9. Based on the theorem that we just covered, because these two segments are congruent, the distance from here to here and from here to here are going to be exactly the same. So 2x equals 5x minus 9. So I'm going to solve it for x. That's going to give me negative 3x equal to negative 9. And when I divide this by negative 3, that's going to equal positive 3. Now, when I use that answer and go back and substitute that for this value right here, 2x is going to be the same as 2 times 3, which is going to be, well, hold on. Pause. No. I found my mistake. My mistake is right here. These ain't 6s. They're 8s. Come on, Osuna. I knew I was doing something wrong. Okay, see, that's what happens when you go too fast. Okay, so 2 times 3, that's going to be equal to 6. All right, so what they want to know is they want me to find the radius of the circle. So they want me to find out what is this distance right here from Q to C. Okay, so let me zoom that in a little bit. So what you have here is you have a right triangle. Okay, you have a right triangle where this distance right here is 6, this one here is 8, and you're being asked to find QC. So one of the things that you could do is you can do Pythagorean Theorem, which we are, and it's going to become an integer because it's a Pythagorean triple. So here you're going to have 6 squared plus 8 squared equal to, I don't know, let's call this radius R. That's going to give me 36 and 64, which is equal to the radius square. Oh, can't see that. And then you are going to combine them to give you 100 equal to R squared. And when you take the square root of that, the radius is going to be 10. Okay, that concludes our lesson for 10.3. Thank you for watching.